Bismillah ar-Rahman ar-Rahim. Hello everyone. This is the second video, but I prefer talking about displacement current. Okay, let's start. As you see now, you have two capacitor plates like this. This is number one, and this is number two. Okay, you know, you see the wire here. Okay, this is the connection to the first plate, and this is the second connection to the second plate. Okay, we are in AC mode, alternating current, and we will try to solve the problem of displacement current, how the electricity can flow, okay, without any direct connection between the two plates, as you see here. First of all, we have to see the magnetic field line, like this here. Okay, now this, see the magnetic field line. It's like circle. It will spread in the plate. You know, for example, if you have a wire like this and you have alternating current, there is a magnetic field circle, okay, across the wire. But when you connect a plate like this now here, the magnetic field will spread, okay, along the plate. Like this. Okay, so what make the alternating current flow in a capacitor? I am trying to explain this physically. Okay, let's see this drawing. Prepare the drawing. Okay, you have a metal like this, for example, and you have an electric field like this. We know the electric field will continue its way. Okay, the magnetic field inside conducting material is zero. Okay, no electric field, sorry, like this drawing here. For example, this is the positive charge here and the negative charge here, and the electric field flow like this. Okay, now this side here will build a negative charge, and this side here will build a positive charge. There is an electric field inside this, but this field here is zero. Okay, and here also is zero. So the metal sheet or plate just conduct the electric field. Okay, but here we have a positive charge and a negative charge. The problem in a capacitor is related to this phenomena. Okay, when the magnetic field turn like this. The induced electric field present here like this circle, okay, but it can't be it can't flow inside the conductor like this. For example, if you let's draw another, okay, you see this, the induced electric field is circle like this. But if if this field continue to flow inside the conductor, this means I have a positive charge here, for example, and a negative charge here, okay, and this is impossible to happen, okay. The electric field can flow from this side here to this side because we have a positive charge separated here and another negative charge separated here, but it can't flow like this. It can't build an opposite charge on the same surface, okay. This is impossible. So what happened? Let's see this drawing, okay. When the induced electric field face this problem, what this field will do? It will build another additive elementary voltage. Let's explain this carefully because this is very very important, okay. There is no electric field here, don't exist at all, okay. So the first field will flow like this and he will find let's draw another magnetic field circle, or sorry, like this here, okay. This field here will exist only in the surface, okay, but not inside the conductor. No electric field here, no, zero. This field will find another value because there is another magnetic field circle here, okay, and another value and another value and another value, but it will build an additive electric field. But not only this, because this field will close the loop. This don't mean it will be from this point to this point and stop. No, it will close the loop, and we will see later how this will be done, okay. Like this, for example, this is another drawing, and here and here. Let's see what I am drawing here. Okay, this field will, for example, start from this point and build an additive electric field charge, okay, but it will find a little value is in some point. For example, let's see this this way. Okay, this explains something important. Okay, the value of induced electric field can be given by this relation. Okay, if this distance here, for example, is very small, the value will tend to be 0. Okay, so we have a maximum induced electric field here. Okay, and we have a minimum. In reality, this induced electric field, I call it a dynamic side. Later I will explain this, why this field is dynamic, because it has two components, one dynamic and the other is static. For example, let's see this drawing. When you have this max and you have this point as minimum, okay, it will be here, okay, but let's explain. Don't focus on the direction, because I am explaining the idea in general. Okay, if this is a max value of induced electric field, this side here is the static. Okay, this is the static side, and this is the dynamic side. It will build okay, let's continue talking. Let's change the direction for better understanding, because I know it will be confusion a little. Okay, or that change the color to green, for example. Okay, this the minimum value, and this is the maximum. Okay, the positive charge, the maximum positive charge, for example, will be built here in this side. Okay, in the edge of, and when we move to the center, the charge will be little. Okay, so this field, this positive charge will generate electric field, static electric field now. Okay, this is a static electric field. In this picture, I am trying to explain how the electric field, the induced electric field, is able to create a static electric field and a dynamic electric field, the two at the same time, without any problem. Because when this field will face the problem in the fall, because it's not able to make its circle inside the fall, it will find another way. You have to find another solution, and sometimes I see this like intelligence. The nature is intelligence. It's not like some people think. So this field will find the solution to this problem. So it will build an additive elementary voltage like this. Okay, and static charge will be built here and will make an electric field like this here. In this side, number 2, opposite thing will happen. Okay, it will flow like this and flow like this and will return. As we said before, this point here, the diameter here is very small, so the charge here is almost zero, so there is no charge. Okay, but it's a way to flow from this point to this point, just to close the loop. Okay, and when this field arrives to this point here, it will flow to the other side of the first plate. Okay, like this, and like this from here to here to here, and finally flow in the same direction. So the magnetic field here, sorry, the electric field here, the static electric field here is zero. There is no static electric field here. Okay, but the most electric field will be positive, for example, like this. Okay, and this zone here will have little charge, and here it have maximum charge. For example, now here is negative, and now here is negative. Okay, let's see another drawing to see how this field is created. The maximum charge is here and will be small when we move to the center, and will be here almost zero, so no electric charge here at this point. Okay, this is the plane. As you see, this is the first, and this is sorry, this is the first, and this is the second. Okay, and the magnetic field will be like this, and this is just explanation drawing. It's not accurate. Okay, let's see how this electric field, this induced electric field work. For the first time, this is start from this way, from the small size to the highest for here, and number 2 now here, number 3, and number 4, and number 5, number 6. Okay, and number 7 and number 8. This is the final stage. When this magnetic field do this, when this induced electric field do this, it will try to close the circle. What does this mean? Because we know the induced electric field flow in circle, it can't be open. okay. But the problem in a capacitor, this field will be opened, okay, because there is a magnetic field and the induced electric field here, okay. It will be opened because there is no field here, so he will build a dynamic side like this, okay, with the highest charge here and the minimum charge here. So this field in a capacitor, it will, for example, it will start this point building elementary voltage, and when this elementary voltage create charge, okay, because we have a minimum and a maximum, there is a charge, okay. Now the static electric field will be flow like this, okay, to the negative side here, and return to the minimum side here, and to this point, okay. But it will not stop here. This field have to continue its work like this, and like this, and like this, and like this. Why? This is very important to understand why this happened, okay. In reality, when this field do this, he will trying to close the loop, okay, like this, because if we see the magnetic field here and the induced electric field, for example, for this point, it is open, okay. He has a half side, okay. The other half side have to be completed in this point. You have to close the loop in symmetry point according this point, okay, because it start from here, okay, and this induced electric field is open and go to the change to static field and to this direction and here. But when we arrive to this point, the loop is still open, it's not closed, okay. You have to pass to this point. If he passed to this point, he has to close the loop like this to the same direction and continue to make the static field here and here and here and here, and finally he'll be here, okay. This is the induced electric field circle example. If this is the magnetic field here, okay, and this is the induced in white, this is the induced electric field. We see this field like this. It has a dynamic side and a static side, okay. But for example, if we see this point here and we try to see, we will see this side look like, I don't mean it's sure, but because we don't know the third element, it's very difficult. I mean it's look like the static side. It can be a dynamic side in other position, and vice versa. Okay, this dynamic side can be static side. So this field is very very strange, and it's very difficult to understand how it acts. But I have done a very small experiment in the extended Tesla bifilar coil. Okay, like this. Show me a strange character. For example, if you take the point A, B, and C and D, if you have a high voltage DC pulse, okay, and if you make the spark gap in CD in this position, in reality I discussed this in the forum, energetic forum, and I said if you, for example, connect your high voltage source, I have to choose another color. Okay, that's red, for example. No, it's not red, it's this one. If you connect high voltage DC pulse to this direction, you find the capacitor, it will be charged very quickly, compared if you for example, if you charge this device from this point, from CB, you have it take a long time compared this side. This is really strange. You can see this by the firing of spark gap. The spark gap from this side, for example, fire very quickly compared this side. This means the capacitor in this side can be charged very quickly compared this side. So this is really strange. There is the only explanation to this phenomena is this, as I was talking before. Okay, what does this mean? For example, if you have two plates like this, this is a normal capacitor, okay, and you connect this capacitor from this point, not here as we said before. Okay, in some situation this capacitor can be charged very very quickly compared if you, for example, try to do something from the above point. Okay, the explanation for this is the formation of electric field, the induced electric field and the magnetic field. The magnetic field here will be like this. Okay, so he has a minimum side here and a maximum. This field look like a polarized magnetic field. Okay, so there is a side where the induced electric field will meet a long way. Okay, for example, if you have this circle and you divide it into two, you see, for example, here you have V value and here you have V value. Okay, but the sum circle, if you, for example, have this circle and you start counting from this point to this point, you have 2V. Okay, So this is explanation and disprove the induced electric field build an additive elementary voltage the same as the extended Tesla bipolar coil. Okay, anyone can try this experiment. It's very simple, and he will see what I'm talking about. Okay, so this is the explanation. The induced electric field will be, he can't as I said before, he can't flow inside an inductor. Okay, so he prefer this way, and he will meet another friend, so he can build a high value from this point, for example, until this point. And this explain why this field, why the capacitor in some condition can be charged very quickly. Okay, that's all. Okay, I hope I will make another video about the mixed extended Tesla bipolar coil, and I hope to receive your question in the forum. Thank you very much for watching. If you like this video, if you find it interesting, you can share with your friend. Thank you very much, and good night.